Hello students, welcome to my YouTube channel Rapid Chemistry. Last day we have had a discussion on the structure of atom, the basic understanding, and that what we have already got in the class 10 level. And today we will enter into the main topic, and for that we have to know the atomic spectra. Atomic spectra and atomic spectra is largely depending on the structure of atom, and to know the structure of atom clearly we have to know atomic structure. So let's start. We have already seen that Rutherford's atomic model failed to explain the atomic spectra and stability of an atom. In order to investigate the reasons behind the failure of Rutherford model, scientists felt that need to explain the nature and origin of atomic spectra. Atomic spectra results from the electromagnetic radiations emitted by the excited atoms, and how I will show. These electromagnetic radiations can pass through vacuum also. According to Newton and the other physicists, light is something but a stream of very small particles. The phenomena of reflection, etc. can be successfully explained using Newton's theory, but those like dispersion, interference, etc. cannot. Thus, particle nature of light was replaced by wave nature of light. In the year of 1865, Maxwell wave theory given. And according to this theory, light is transmitted in the form of electromagnetic waves, and these waves are associated with oscillating electric field and magnetic field. These two fields are perpendicular to each other and also to the direction of propagation, and as shown in the figure here. Unlike sound waves, electromagnetic waves do not require any medium for their propagation and can travel in vacuum. So the theory given by the Maxwell has been shown here. The electromagnetic wave and the electromagnetic wave has been shown here, and the two fields, that is one electric field and one magnetic field, and they are perpendicular to each other and also to the direction of propagation. As shown in the figure here, in the plane of the paper, the magnetic field has been shown, and with the vertical way of the paper, that is perpendicular to the paper, the electric field has been shown. So that is the combination effect of electromagnetic wave. In our day-to-day life, we are familiar with the terms electromagnetic wave and its different form, and the different types of electromagnetic waves such as X-ray, visible light, radio waves, etc. are there. The full chart is there, and I will definitely show you here. Let's look at the another figure where electric field and magnetic field has been shown nicely, and they are perpendicular to each other, and they combinedly forming electromagnetic wave. Now we shall discuss some quantities related to electromagnetic radiation, and the very first one is wavelength. And wavelength is shown by the sign lambda, and say it is an wave. And it is the distance between any two consecutive crests and or troughs of a wave. So that is the distance of a wavelength, complete wavelength, and the common unit we are using for wavelength, that is angstrom, nanometer, centimeter or meter, and these units are related by this simple relation. And the next one is frequency, and the frequency, it is the number of wave passing through a particular point in 1 second. In 1 second, and the unit is cycles per second or hertz, Hz. So, and the velocity of the electromagnetic wave, it is the linear distance traveled by the wave in 1 second. 1 second. In 1 second, if the number of oscillation and is that is the frequency has shown by a term, and that looks like V, and it's not V, it is nu. And the wavelength lambda, that is for each oscillation or frequency, the distance moved by the wave is lambda. So for lambda, so the velocity of the wave should be, nu into lambda. Okay. And for the electromagnetic wave, the velocity is fixed, and that is the speed of light, 3 into 10 to the power 8 meter per second. And the visual light, the visible light is also a electromagnetic wave, and the unit centimeter per second or meter per second. And another important term is the wave number. So wave number of waves formed in 1 centimeter of length. So, and that is mathematically found to be nu bar. It is to be shown by like this: nu bar mathematically 1 by lambda, and 1 by lambda is also found to be nu by c, and where c is the velocity of light or speed of light, as we are saying, 3 into 10 to the power 8 meter per second. So these are the common terms which are very important, and to understand the electromagnetic wave, the first one is wavelength, and the second one is frequency, third one is its velocity, and the fourth one is wave number. Okay. Now we will study electromagnetic spectrum, and here the complete electromagnetic spectrum has been shown. Okay, and let's define the electromagnetic spectrum. Arrangement of all the electromagnetic radiations. Arrangement of all the electromagnetic radiations. These are the different electromagnetic radiations in the increasing order of their wavelength. Increasing order of their wavelength. Wavelength is increased from, left to right. Okay. Or decreasing order of their frequency. Frequency is decreases from left to right, is called the electromagnetic spectrum. So it is the electromagnetic spectrum, and the electromagnetic spectrum, and here it is written, and generally it is to be shown like this. So what are the different kind of rays which are constituting the electromagnetic spectrum? So that is the gamma ray, X-ray, UV, IR, microwave. Okay, and there is long radio wave and the radio wave. Radio wave is there, FM or AM. The two differences are there. Different kind of radio waves are there, and just try to understand one thing here. So if it is the total complete electromagnetic spectrum, only a very small part has been taken as visible range, and that is the visible spectrum. That means our visible world is very small in compared to the invisible world. So that is the invisible part. UV, X-ray, gamma ray, okay, all these are invisible. And the IR, micro, FM, AM, long radio, all these are invisible. But their presence has been proved many times, and we are in our day-to-day life, we are using these rays in different way, and I will discuss all those. Okay. So the visible spectrum, only a very small part of the electromagnetic spectrum. Okay, and in the visible spectrum, almost the starting from left to right, VIBGYOR, violet, indigo, blue, green, yellow, orange, red. Okay, and it lies within the range of 400 nanometer to 750 nanometer. Okay, so you all have to remember all the electromagnetic rays in the proper order. No need to remember all their wavelength and the frequency, but you have to know the wavelength. Okay. Now let's look at the uses of different electromagnetic rays. Like gamma rays are used in cancer treatment, X-rays are used in medical pictures and material testing, ultraviolet rays are used in germicidal lamps, visible light, and that is the light or rays which can make an object visible. Infrared is used for heating purposes. In microwaves are used in cooking and radar, and the radio frequency used in signal transmission, that means in television and the mobile we are using. In spite of having so many positive aspects of electromagnetic wave theory, and there exist some limitations. So here we will study the limitations of electromagnetic wave theory. This theory successfully explained the properties of light such as interference and diffraction. However, it failed to explain the phenomena such as black body radiation, photoelectric effect, line spectra of atom, variation of heat capacity of solid as a function of temperature. So, and in these aspects, the electromagnetic wave theory is not sufficient enough and we need a better theory. And here we will not discuss the black body radiation or photoelectric effect. Those are there in the modern physics in class 11-12, and as we will stick to the subject and here the structure of atom, and we have to study line spectra of atoms and what does it mean, and I will discuss in details line spectra of atoms. Now we shall discuss some problems based on the relation C equals to nu lambda. C equals to nu lambda, okay, or or nu equals to C nu bar. Nu bar means 1 by lambda, okay, and that is the wave number I have said right now. So say one problem is there. Yellow light emitted from a sodium lamp has a wavelength given 580 nanometer, 580 nanometer, and if you know the relation between nanometer and meter, so you have to multiply with 10 to the power minus 9 to make it meter. So that is the wavelength, that is lambda value given, and the C value, that is the speed or velocity of light, is known 3 into 10 to the power 8 meter per second, and that is the value which can be applied for all the electromagnetic radiations, okay. And now frequency you can find out simply, okay, and once frequency is known, that the wave number of that radiation can also be found, and the wave number has been defined, the reciprocal of wavelength. So hopefully you got the very first one, okay. Come to the very second one, the example, and here, okay, the wave number of a beam of light is given, that is nu bar is given. So nu bar is nothing but 1 by lambda. So if nu bar is given, we can find out lambda, and once you know the lambda, okay, and you can find out frequency from the relation C equals to nu lambda, and thus you got the value, okay. And a similar problem is there, and just to go through it, okay, and definitely you can understand, and if not, I will definitely help you here, okay. Now we shall study the particle nature of electromagnetic radiation, Planck's quantum theory. The failure of the classical electromagnetic theory of radiation to explain the phenomenon of photoelectric effect led by Max Planck in the year of 1901 to propose a new theory known as quantum theory of radiation. Quantum, the term is related with the particle quanta, okay. The main points of this theory are, okay, that means classical electromagnetic theory is not sufficient enough to explain all the phenomenon, and that's why in the year of 1901 the German physicist Max Planck proposed a new theory, and that has been celebrated in the history of physics as a quantum theory of radiation. And this theory states that number 1, the radiant energy is emitted or absorbed not continuously but discontinuously in the form of small packets of energy called quanta. Okay, so what does it mean? It means that you are getting certain amount of heat from somewhere else, okay. So the whatever the heat energy is coming to you, and that is not coming continuously but discontinuously, okay, in the form of a large number of small packets of energy, and those packets of energy has been named as quanta, okay. Each wave packet or quantum is associated with definite amount of energy. In case of light, the quantum of energy is often called photon. The second one here is the amount of energy associated with the quantum of radiation is proportional to the frequency of radiation. Frequency of radiation is proportional with the amount of energy associated with each quantum, and proportional to nu, okay. So nu is the frequency of the radiation. So we can have the simple equation E equals to h nu, where h has a constant and that has been taken as Planck's constant, and you have to know its value, 6.625 or 26 into 10 to the power minus 34 joule second in SI unit. Okay, and that equation can be modified like this. Look at here. So we have studied already in this video, that is, in the place of nu you can write c by lambda. So another form of the equation has been derived. Okay, and then number 3 here, a body can emit or absorb energy only in terms of the integral multiple of quantum. That means, and wherever certain amount of energy is released or absorbed, okay, so that must be the integral multiple of certain number of quantums. Okay, so n number of quantums can be there for certain amount of energy. So n must be whole number. Okay, so this means that a body can emit or absorb energy as h nu, 2h nu, 3h nu, like this. Okay, so these are the main 3 points regarding Planck's quantum theory. Okay, just mark this point. The energy possessed by one photon is called one quantum. The energy possessed by one mole photon is called one Einstein. Okay, and the one Einstein and has been found to be, that is n0, that is n means Avogadro number or that number of quanta. So one Einstein energy equals to that much. So after the Planck's quantum theory, it has been proved that the electromagnetic radiations are not only the having wave characteristics, it also having particle characteristics, and that's why dual nature of electromagnetic radiations has been given. Okay, and for that, and we will derive a simple equation. The energy of a photon is given as E equals to h nu, and also according to Einstein equation we know E equals to mc square. And if you combine these two equation, and simply you can do h nu equals to mc square. Okay, you all are requested to do this kind of derivation by yourself. Okay, just do not just watch. Okay, just do and watch simultaneously. So, and here combining these two equation, we are getting that one. Okay, so that one, m equals to h nu by c square, and another form is there, m equals to h by c lambda. Okay, so that is the equation, and which shows the dual nature of electromagnetic radiations. And from that equation, and we can have one or two numericals. Let's look at here only. Now let's study one or two numericals or problems based on the Planck's quantum theory. Calculate and compare the energies of two radiations, one with wavelength 400 nanometer and the other is 800 nanometer. Two radiations are there and we have to compare their energy. Okay, and let's see how they did it. Okay, so E equals to h nu. H, that is the Planck's constant value that is known and to us right now, and the c, that is the speed of light, and only the value for lambda is, in the case of the first one, 400 nanometer, that is 400 into 10 to the power minus 9 meter, that is the E1. Similarly you can find out E2 and then have the ratio. Okay, let's look to another problem here. Okay, find the energy of each of the photons which correspond to light frequency is given. So I hope you can do this kind of numericals. Just move it first here. Okay, one more here. What is the number of photons of light with wavelength 400 nanometer? Okay. Okay, just to go through, and I hope you can understand these are. Okay. Now we shall study emission and absorption spectra. When light or any other electromagnetic radiation is made to pass through a spectroscope, the light separates into various components of different wavelengths, producing various colored bands. The set of colored bands formed is called spectrum, and the spectra can be of two types, emission spectrum and absorption spectrum. And how it is formed, I will show you right now. Okay. This is the continuous spectrum formed by white light. Okay, so white light is there and that is allowed to fall on a prism, and after refraction, and there will be the separation of all the 7 colors of white light, and those are found in a photographic plate. Okay, and deviation is maximum for violet, so the ray was in that line, so maximum deviation for violet and the minimum deviation is for red. Okay, so and a continuous band of 7 colors are obtained, and that is said to be the continuous spectrum. Okay, now here we will study how line spectrum can be formed. And take hydrogen gas in a discharge tube at very high voltage. H2 gas will dissociate to hydrogen atom and they will excited, and whenever they will excite, and they will release energy, and of all those energy is allowed to fall on a prism, and there can be spectrum. Okay, but that spectrum is different that from the solar spectrum, and here the colors are there at different places. That is, this spectrum is not a continuous one, and that is the line spectra, and that's how line spectra is obtained. And the line spectra tells a lot about the structure of the atom. Okay, and we will definitely learn those step by step, and that's why here it is written. Just go through this line. Therefore, the atomic spectrum of an element can be used to identify the element, and it's sometimes called fingerprint of its atoms. Okay, so what kind of spectrums are obtained, and just explaining all those the characteristics of the spectrum. Okay, we can know the nature of the atom and its characteristics. The spectrum obtained here, and that is the line spectrum, and the line spectrum okay, and that is emission spectrum. It is actually, this is the emission spectrum, and there can be another kind of spectrum, and that is absorption spectrum. And because so in here the absorption occurs, that is whenever white light is allowed to fall through, say, NaCl solution, and the NaCl solution will absorb a part of it. Okay, and and another light is coming to prism here, and you are getting in the different and radiations here. Okay, and another spectrum is obtained, and that is said to be absorption spectrum. So spectrums are of two types, and the one is emission spectrum and another is absorption spectrum. And now you have to compare this kind of two types of spectra. Okay, so emission spectrum. So emission spectrum is obtained when the radiation emitted by the excited atoms of a substance are analyzed in a spectroscope, and it consists of colored lines separated by the dark spaces. The emission spectrum of white light is a continuous spectrum. But what about the absorption spectrum? Look at here. It is obtained when white light from a heated incandescent and substance is made to pass through a liquid or a gaseous substance. Okay, and the emerging radiations are then dissolved in a spectroscope. Number 2, it consists of dark lines in the otherwise continuous spectrum. Absorption spectrum is always a discontinuous spectrum. Now we will start the hydrogen spectrum. That means whenever taking hydrogen gas in the discharge tube, and the light, as I have said, in the discharge tube, hydrogen gas is dissociated to hydrogen atom, and they are excited, and in their excitation they will release energy, and those energies, whenever allowed to pass through prism, we are getting and the spectrum, and the spectrum is not a continuous one, and this is a discontinuous one. Okay, and this is emission spectrum of hydrogen. And whenever emission spectrum of hydrogen and has been and explained by different scientists, and they got different lines, and the lines are these are the different lines they got. Okay, the Lyman series, Balmer series, Paschen series, bracket series, the phone series. So these are the different lines obtained, and they combinedly forming the spectrum for hydrogen. Okay, so and generally out of all these, only Balmer series lies in the visible range. That means those can be detected by human eyes, but the rest are not. So just look at the chart here. That is the different kind of emission spectrum of hydrogen, and often the 5 series are there: Lyman, Balmer, Paschen, bracket and Pfund. Okay, so the Lyman series lies in the UV region, Balmer series is only the visible region, and the rest are in the infrared region. In the year of 1885, the scientist Balmer showed in the spectral lines are expressed in terms of wave number. Okay, and that is the wave equation, and the Balmer had given. That is the new word, that is the wave number. A constant is there, that is said to be Rydberg constant. Okay, that is said to be Rydberg constant, and that is for the equation is applied for Balmer series. For the Lyman and for other series, the nature of the equation will change a bit, and how it is I'm showing here right now. So that is the line spectrum of hydrogen atom in visible region. Visible region, the visible region lies in between 3800 angstrom to 7600 angstrom, and within that these are the spectrum obtained, line spectrum of hydrogen atom. Okay, and these are the lines obtained. The violet, blue, bluish green and the red are obtained in the different range. In the year of Balmer 1885 gave this equation for this is and it is said to be wave equation, and wave equation, and that is nu bar. The nu bar equals to 1 by lambda. Okay, that is the reciprocal of wavelength. R is the Rydberg constant, and 2 is the that is the cell in which the electron are falling from higher cell, and N is the A cell from which the electrons are falling. So how it is forming, and I will show here right now. Okay, let's try to understand this figure. 6 series of spectral lines in hydrogen and spectra. So these series of the different series are obtained whenever one excited electron jumps from higher cell to lower cell. Okay, so the Lyman series is obtained whenever any electron jumps from any higher cell to the first cell. The Balmer series obtained whenever an electron jumps from any higher cell to second cell. The Paschen series is obtained whenever an excited electron jumps from any higher cell to third cell. Okay, the bracket series is obtained whenever an excited electron jumps from any higher cell to the fourth cell. Okay, and thus the Pfund and Humphreys series are obtained. So these are the 6 series of spectral lines in hydrogen spectrum. Okay, and these are the values, the n equals to 1 2 3 4 5 6 7, and these are the fixed orbit around the nucleus. This is the very important chart here, that is the different series and their that is the equation, wave equation, and the range in the spectral region. So only one is there in the visible range. Okay, and there, and you have to understand, so n1 and n2 value. N1 means the cell in which electrons are coming, and the n2 is the higher energetic cell. That means whenever one electron jumps from to the second, third, fourth or fifth cell to the very first cell, okay, so the Lyman series obtained, as I have said right now. Okay, and if one electron jumps from third, fourth, fifth or sixth cell to the second cell, so you are getting Balmer series. That means in all the series for the hydrogens are obtained for whenever one excited electron jumps from higher cell to lower cell. Okay, higher cell to lower cell. So that is the in this equation. So the here, that is the lower cell, that is the electron where it is coming from the higher cell, and the higher cell number is that one. Okay. Okay, look at the one problem given here, and that would be very clear to you. Okay, and you have to remember the different series and their wave equation and the spectral region in which they belong. Okay, now come to the one numerical as given here, and that will give you clear understanding. So calculate the wavelength of H alpha and H delta in the emission spectrum. Now it is to be informed you that H alpha and H delta, what are these? Actually these are the H alpha and H delta. Let's look at here. As I have said, that is for the line spectrum of hydrogen atom in the visible region, that is the Balmer series, that mainly the four important lines are there: one red, bluish green, blue, and the violet. And the red one is said to be H alpha, and that one H beta, H gamma, and H delta. Now our question will deal with this one, H alpha and H delta. So these are formed whenever look at here only. So Balmer equation, wave equation is that one. That means one electron jumps from higher cell to second cell. Okay, so higher cell to second cell. Whenever one electron jumps from third cell to second cell, we are getting H alpha. Got it? Okay, and whenever one electron jumps for fourth to second, then H beta, then fifth to second H gamma, and whenever one electron jumps from sixth to second cell, we are getting H delta. So N1 value and N2 value. Okay, so that's how they did it. Okay, and that one R is a Rydberg constant and its value is a constant 109678. So how that equation came, and I have not discussed that one yet, and even in your book. Okay, and we will definitely discuss that one in the next class, how the equation has been derived.